Having articulated how the interplay of the 10th and 11th dimensions generates universal waves that sculpt the large-scale structures of the cosmos, we now turn to a phenomenon that has baffled physicists for nearly a century, the double-slit experiment. This seemingly simple experiment, conducted with particles as fundamental as photons and electrons, vividly demonstrates the perplexing wave-particle duality and the measurement problem, pushing the boundaries of our intuition about reality. Our 11-dimensional model offers a profound reinterpretation, suggesting that the double-slit experiment does not reveal a particle's inherent wave nature, but rather unveils the fundamental universal wave itself, demonstrating its inherent probabilistic nature and its interaction with the lower dimensions upon observation. The double-slit experiment's setup is elegantly simple. A source emits particles, for example, photons or electrons, towards a barrier containing two narrow slits. Behind the barrier, a screen records where the particles land. Classical expectation. If particles were tiny billiard balls, we would expect to see two distinct bands on the screen, directly aligned with the slits, as if some particles went through one slit and others through the other. Wave behavior. However, when the particles are observed collectively, an interference pattern emerges on the screen, alternating bands of high and low intensity, characteristic of waves like water waves, passing through two slits and interfering with each other. The measurement problem. The mystery deepens when we try to observe which slit a particle goes through. If a detector is placed at one of the slits, attempting to pinpoint the particle's path, the interference pattern vanishes, and the particles behave like classical particles, forming two distinct bands. The act of observation seems to collapse the wave-like behavior into particle-like behavior. This measurement problem, or observer effect, has been a central enigma in quantum mechanics, suggesting that reality at the quantum level is intrinsically linked to observation and probability, rather than a fixed objective state. Conventional interpretations attribute the interference pattern to the particle's own wave function, describing its probability cloud spreading through space and interfering with itself. The collapse of this wave function upon measurement is often described as the instantaneous reduction of possibilities to a single actuality. Yet, the question of what exactly collapses and how or why observation triggers this remains a subject of intense debate and philosophical speculation. Our 11-dimensional model offers a revolutionary alternative to the particle-centric view of the wave function. We propose that the interference pattern observed in the double-slit experiment is not a manifestation of an individual particle's wave function, but rather the direct expression of the universal wave itself, the omnipresent dynamic interplay between the 10th dimension and the 11th dimension. The particle as a localized manifestation. In this view, a particle is not the source of a wave, but rather a localized, temporary manifestation or condensation of the universal wave in the lower dimensions. It is a point where the inherent probability of the universal wave temporarily coalesces into a deterministic presence. Particles are, in essence, highly stable interference patterns within the universal wave, reflecting its fundamental topology. The slits as dimensional filters. When these localized manifestations of the universal wave are aimed at the double-slit barrier, the slits act not just as physical openings for particles, but as dimensional filters or apertures for the universal wave itself. The universal wave, which continuously permeates all 11 dimensions, is forced to propagate through these two narrow openings. Interference as the topology of the universal wave. The interference pattern observed on the screen is thus a direct visualization of the topology of the universal wave as it passes through the two slits. Just as water waves interfere when passing through two gaps, The fundamental oscillation between the 10th and 11th dimensions interferes with itself. The constructive interference regions on the screen are where the expansive and contractive aspects of the universal wave align synergistically, leading to a higher probability of observing a particle. The destructive interference regions are where these dimensional forces cancel each other out, resulting in a lower probability of observation. Each particle then lands at a point dictated by the underlying probability landscape of this universal wave, which has itself been shaped by the slits. The particle never truly goes through one slit or the other. It is the underlying universal wave that passes through both, and the particle emerges as a localized effect where the wave's amplitude is highest. The most perplexing aspect of the double-slit experiment, the measurement problem, finds a profound and intuitive explanation within our model. When a detector is placed at one of the slits, attempting to observe which path the particle takes, the interference pattern vanishes. Our model reinterprets this not as the collapse of a particle's wave function, but as the localization of the universal wave itself into a deterministic manifestation in the lower dimensions. Observation as imposition of the 10th dimension's dominance. The act of observation or measurement involves a highly interactive process. A detector, by its very nature, is a system designed to register a specific, localized, deterministic event. This detector system primarily operates under the influence of the 10th dimension's deterministic force. When the universal wave interacts with such a 10th dimensional dominated detector, the inherent probabilistic nature of the 11th dimension is momentarily suppressed or localized. The 10th dimension's deterministic aspect gains temporary dominance. Instead of collapsing a particle's wave, the observation forces the universal wave to localize its manifestation through one specific slit. The probability field of the 11th dimension, which normally allows the wave to explore both paths simultaneously, is constrained by the deterministic interaction with the detector. The universal wave chooses to manifest its energy and information through one discrete path, thus solidifying its presence as a seemingly classical particle in the lower dimensions. The probabilistic nature of quantum events, you see, is a direct reflection of the 11th dimension's inherent influence within the universal wave. Now, before observation, the universal wave exists in this superposition of potentials, embodying all possible outcomes at the same time. The probabilistic distribution on the screen, when there's no detector present, is simply the inherent topological patterning of the universal wave itself, reflecting the varying potentials for localization. Upon observation, this vast field of 11th dimensional potentials is, well, forced into a singular deterministic outcome by the 10th dimension's dominant influence during the measurement process. The wave function collapses not because of some mystical influence of consciousness, but because the interaction with the 10th dimensional dominated measurement apparatus forces the multifaceted 11th dimensional potential to localize into a single observed reality. This reinterpretation resolves several conundrums. The particle never possesses an inherent wave function. It is merely a localized bump in the universal wave, the mystery of which slit vanishes because it's the wave, not the particle, that traverses both. And the collapse is not arbitrary, but a fundamental dimensional interaction. The deterministic 10th dimension's dominance over the probabilistic 11th dimension at the point of measurement, forcing a singular observable outcome from a field of potential. The double-slit experiment, therefore, becomes a powerful empirical demonstration of the dynamic, ever-present interplay between cosmic expansion and cosmic contraction, shaping the very fabric of reality at every scale. This concludes the third part of our essay, where we have applied our radical reinterpretation of the wave function to the double-slit experiment. The next and final part We'll discuss the profound implications of this new understanding for quantum mechanics cosmology and the very nature of matter, along with the challenges and future directions of this dimensional framework.